Hello class, Mr. Stemple here with your second discussion on beams for both IED and POE class. So let's talk about what we're going to do today. Today we're still working with I-beams, and we're going to learn why I-beams or hollow beams are more commonly used than solid beams based on cost and relative strength. So your assignment for POE is to do the calculations. Just follow along with me. Do the calculations in your notebook. You're going to be calculating the moment of inertia for a solid and an I-beam. You're going to be calculating deflection for a solid and an I-beam. And for IED, your assignment is to do the drawings in your notebook for both a solid beam and an I-beam along with those calculations. So let's jump right into it. As a review, that's right in my face. As a review, we talked last week about beams and columns and what the differences were. We talked a little bit about deflection. We talked a little bit about what beams do and how they hold the weight or the forces that are placed on them. And we talked a little bit about the maximum deflection equation, which looks like a tough equation, but it's really not too bad because this is force and length and modulus of elasticity, which is a constant, and then of course moment of inertia, which we calculated, or which we will calculate this time. Now let's get into the calculations. Before we get there, let's talk about the beam types that we're going to use. We're going to talk about a solid beam, and then we're also going to talk about an I-beam. Now the I-beam, as you all learned during the quiz last week, which was to read some articles on I-beams and to learn a little bit about them. I-beams have some distinct characteristics. There's the web, that's the piece in the middle, and the flanges on top. They're designed to be used in that configuration, and they're designed to hold a lot of weight and to not have a lot of twisting motion on them. Some standard sizes of I-beams, I found this on the web. Some standard sizes of I-beams are right there below, and we're not going to use the exact standard size of I-beams because there's a lot of decimals in there and it makes the calculations difficult. We're going to use relatively standard size, 30 inches tall by 15 inches wide. And if you'll notice in there, you'll see that the web is very small compared to the rest of the I-beam. So we're going to use a standard web size of 1 inch because that's going to make all the calculations much easier to do. So in your notebook, you should draw both of these things. This is part of your IED assignment. Your solid beam is going to be 30 inches by 15 inches. And your I-beam is going to be also 30 inches by 15 inches, but each piece of the web and the flange, you're going to go ahead and make 1 inch. So when I get my screen back here, I'll show you what mine looks like in my notebook. So take a second, pause the video, and make sure you have both of those drawn in your notebook. That's your IED assignment for today. Make sure you have all the dimensions and everything on it. And here's what mine looks like. So there's my solid beam, and there's my I-beam in my notebook. Alright, now let's talk about the calculations for moment of inertia. Moment of inertia is based on what the cross-sectional view looks like. So if you cut that I-beam in half or cut that solid beam in half and took a look at the end of it, that's the stuff that's used to calculate moment of inertia. And it's the base times the height cubed, so the height 3 times, divided by 12 gives you moment of inertia. So you can calculate moment of inertia for the solid block and for the I-beam, but the I-beam you have to consider it in a different way, and I'll get to that in a second. So the moment of inertia for the solid block is pretty easy to calculate. You just take the base, which is 15 inches, multiply it by the height cubed, and the height is 30 inches, so that's 30 cubed, and then divide that by 12. Pause the video right now, go ahead and do that. I've given you the numbers. Get out your calculator, get out Google, get whatever you're going to use to do the calculations, and go ahead and do that calculation and write it down in your notebook. So then we'll get into calculating moment of inertia for the I-beam, which is a little bit more difficult because you don't have all that same amount of metal in there. Essentially in an I-beam, you're cutting out 2 pieces of metal, one on each side of the web. But you use the same formula. So let's calculate the positive part of the moment of inertia, which is the same number that you calculated in the last slide. So 15 times 30 cubed divided by 12 should give you this number, 33,750. And that's the moment of inertia if I had a solid block of steel. Now let's take out those two pieces on either side. And if we use 1 inch for the width of the web and 1 inch for each of the height of the flanges, then that means that this block in the middle, that piece that I took out here, that negative area, is 7 inches on the top and the bottom. The base is 7 inches and the height is 28 inches. So I can do that same calculation right there. 7 times 28 cubed divided by 12 gives me 12,805. Now to find the moment of inertia for the entire I-beam, I have to take that positive moment of inertia, that 33,750, and then subtract both of those side versions, subtract that 12,805 from both sides, and that'll give me a number. I know that's a lot, and I know I went through it kind of quick, so feel free to back up and listen to it again if you need to. So pause right here and do that calculation and figure out what you're going to get. Put that in your notebook. Remember, all of this stuff should be in your notebook. That's your assignment for today. All right, now that you have all that calculation, you have the moment of inertia for both the block and you have the moment of inertia for the I-beam. We can move on to the next set of calculations, which are deflection. I'll show you here in my notebook. I've got all these calculations. I have the moment of inertia calculation. Over here I've got the deflection calculation. I've got a whole bunch of calculations in my notebook. Your notebook should look similar. So let's talk about deflection now. Remember, deflection is the force that's placed on a beam multiplied by its length cubed divided by 48 times the modulus of elasticity times that moment of inertia that we just calculated. If we want to compare these two beams as if they're the same material and spanning the same length, then a lot of those things are going to be constant. So we're going to compare this beam length. We're going to say that it's a standard length of 100 feet, which, as you know, if you did the quiz last week, you know that 100 feet is the maximum length of an I-beam, just because of the way it's manufactured. And we're going to consider that we want to put 2,000 pounds on top of that I-beam. 2,000 pounds is approximately 1 ton. So we're going to put 2,000 pounds on top of that I-beam. And the modulus of elasticity of steel is roughly 30 times 10 to the 6 pounds per square inch. It's a little bit different than that, but we're going to use that because it's close enough. So all those things are going to be the same for both calculations that you're going to do next. So the F force is going to be 2,000. The length L is going to be 100 feet or 1,200 inches, because remember we're doing this in inches, so we have to convert. And the modulus of elasticity E is going to be 30 times 10 to the 6. So when you're doing these equations, you can basically just plug all those numbers in. So let's start with the deflection of the solid block. And remember, with deflection, what we're calculating is how far down this block is going to bend when we load it up with this particular force. So we're going to load it with a force of 2,000. We're going to span it over 100 feet, which is 1,200 inches. And then 48 is a constant. We're going to multiply that by 30 times 10 to the 6th, which is the modulus of elasticity. And then multiply that by the moment of inertia that we calculated in the last set of slides. So the moment of inertia that we calculated for our solid block, which again is based on its profile, is 33,750. So go ahead and do all that calculation. I know that seems like a lot of math, but it's all right there. Put it into Google, put it into your calculator, figure it out, pause the video until you get an answer, and then resume. All right, now that you've got an answer for the deflection of the solid block, now we'll do the deflection for the I-beam, which uses the same equation. So once again, we calculated the moment of inertia for the I-beam in the last set of slides, and those are the numbers there. You should have those in your notebook. The total moment of inertia for the I-beam is 8,140. And so we're going to put that into our deflection calculation. Again, 2,000 for force, 100 feet or 1,200 inches for the length, 48 multiplied by 30 times 10 to the 6th for the modulus of elasticity, and then multiply that by the moment of inertia for the I-beam, which you should have calculated to be 8,140. Go ahead and put that into Google and calculate what the deflection is for that I-beam. Unpause the video whenever you get a chance. All right, so in conclusion, you should have calculated the deflection of your solid block as 0.071 inches. That means a beam of 100 feet made out of a solid steel block of those dimensions will deflect 0.071 inches whenever you put a ton of weight on it, which isn't very much. If you have the I-beam spanning the same length, made out of the same material, it will deflect 0.29 inches, which seems like it might be a fair amount more, right? 0.29 inches is about a third of an inch, still not very much. Not enough that you're going to really notice it. So the solid block, though, uses 7.75 times more material. That means it's 7 3/4 times heavier, almost 8 times heavier. It's almost 8 times more expensive. It's almost 8 times more expensive to build and to ship and to store and to use, etc., etc., etc. So it's really not worth the extra expense to use that solid block rather than to use the I-beam. Now, in some applications, it might be worth using the solid block, or it might be worth using a smaller solid block. But if we're comparing size to size, generally the I-beam is less expensive. It's much less expensive, and it's less expensive of a factor that it's not worth spending the extra money for a solid block. So let's talk about what you're turning in today. Today you should turn in the POE calculations in your notebook. So all these calculations that you did, turn them in, and you can turn them in by taking a picture and uploading it, or showing it to me in a conference call or whatever. You should have calculations for the moment of inertia and the deflection for both the solid and the I-beam. And for IED, you should turn in the drawings in your notebook for both the solid and the I-beam. Once again, turn those in on a conference call, or take a picture, or scan them, or whatever it is you're going to do to get them up into Canvas. Hope you're all doing well, and look forward to talking to you next week.